because you go from 1 to 5 to 0 to 2, 3 to 12, 4 to 5, 5 to 4. You get the idea. So let's explain the example real quick. I just explained actually. So what's going on in the code? So in the code, we're going to use a priority queue that sorts by the weights of the edges that we have. And it runs a variation of breadth first search, where rather than adding all adjacent edges that haven't been visited, it only adds edges where the path to that node is more optimal than the path that has already arrived at that node. So basically here, right, if we already went from 1 to 5 to 4 to 0, right, and then now we're also going from 1 to 5 to 0, then it adds 0 because this path 1 to 5 to 0 is actually the same, or actually no, it won't add it because it's the same, right? And we only add it when it's worse. So like if I had to go from 1 to 5 to 4 to 2, right? And then if we also if we're also at the node 0 and we find 2, then we do add this to the priority queue because this is more optimal than going from 1 to 5 to 0 to 2 is more optimal than going from 1 to 5 to 4 to 2. And similarly, when it's not optimal, like suppose we already went from 1 to 5 to 0 to 2, and then later we go from 1 to 5 to 4 to 2, this is not optimal, so we just stop our algorithm there and don't go to 2. So let's go through the code. It's in Java. So first we have a distance array that we're going to initialize, right? And initially, our array is full of like infinity, signifying that we haven't reached the node yet. And we set the source is our like source node, right? And we set the distance to 0 because the node to itself is just 0. And finalized is a Boolean array that tells us whether or not the shortest distance to that node has been obtained. So this part of the code sets up a priority queue for Dextras that stores the pairs, which is the total weight in the path so far, as well as the current node. So we also add the initial pair to the priority queue, which is a pair that has total weight 0, and it's at the source node, right? As you see here, 0 source. And let me explain a bit what's going on over here, so in case you don't know. So we have a new priority queue full of these pair integer, right? And this first parameter is the size, and we know that the priority queue won't be like the size of it won't be greater than n, so we can just assign it n size at the start, right? And this right here is a comparator. Basically, it's sorting by a dot key minus b dot key. So the first number of the pair. Key is the first number, value is the second number, right? And essentially, this is just like, it's called lambda, and it's basically just a more concise version of a comparator. Normally, you would do public int compare, and you return a dot get key minus b dot get key, right? But here we're just doing that like in a more compressed shape. So hopefully you understand this. So okay, this is like the main part of the algorithm, which is like the while loop that iterates through the Dextras, right? So while the queue is not empty, similar to BFS, you just keep continuing the loop, and you take the pair with the lowest weight, and you check if it has already been finalized. If it has, then you just skip it, right? We don't need to keep going on it, keep trying to optimize it because we know it's already the shortest distance there. And if it's not finalized, then we proceed with the code. And if the distance is still infinity, then we know that like something went wrong. So we can just break out of the loop. And you'll see why we break out when it's still infinity in a second here. And since our algorithm is greedy, right, and we keep taking the shortest or the node with the shortest path, total weight of the path so far, right? As soon as we reach a node, we know that the distance to there is the shortest distance that you can get to there from, right? Because we take the shortest weighted path each time. And yeah, that's why as soon as we reach a node, we finalize it, because we know it's already the shortest path to get to that node. And the last part, which is adding stuff back into the priority queue. So essentially, we just iterate through all the edges that are adjacent to the current node, right? And basically, J just takes the first attribute of the edge, which is the point, the end point, right? And weight takes the second attribute, which is just the weight of the edge, right? And if the distance plus the weight is less than the distance of the endpoint, then we simply set the distance of the endpoint to our current distance plus the weight of the edge, and we add this back to our queue. So I'm gonna go back to here real quick and show like a general overview of what would happen. Right. So basically, after we get, so I think I have okay, yeah, I'll just go through like what would happen here. So we start at node 1, and the priority queue consists of nothing except a node with 0 total pathway so far and source of 1, right? So now we find 5 in here. The distance to 5 is still infinity. So we know that 0, which is our current weight, plus 4, which is the edge weight, is less than infinity, right? So we simply initialize this 5 with the dist to 5 with this to 1 plus this weight, like what happened here in this code, right? If distance I plus the current weight of the edge is less than the endpoint of the edge, then we simply set the weight of the endpoint to the current one plus the weight, and then we add it to the priority queue, right? So now that 5 has been replaced, we can add 5 to the priority queue. And now our priority queue consists of a node 5 with total weight 4, right? Because our weight so far to 5 is 4. So then we take the least weighted pair in the priority queue, which is only 1. So we take this, and then and then we iterate through all the neighbors. So first, let's go to 0, right? We know 4, which is our current weight at 5, plus this 5 of the edge. 5 weight of the edge is less than infinity, which is what 0 has. So we add 0 to the, we replace the distance of 0 with 9, and we add 0 to the queue. And now we're still not done traversing the edges of 5, or the neighbors of 5, so let's go to 4 as well, right? And 4 is the same situation. We have 4 plus 1 less than infinity, so distance 4 equals the weight 4 plus edge weight 1, which is 5, right? And we can't forget to go back to 1 as well, because of course it's a neighbor. And when we try to go back to 1, we see that the distance 4 plus this edge distance of 4 is greater than 1, right? So we don't want to touch this and do unnecessary iterations. So we just skip this. Like, if this only when the distance plus the weight is less than our endpoint distance, do we add the pair to the queue, right? If it's not, then as you can see, we just do nothing. So after we have 0 and 4 in the queue, right? 0 has weight 9, 4 has weight 5, right? 4 comes first since it has a lower weight. So the 4 tries to go to 0, but this is 9 and this is total 5 plus this weight 4 is not less than this. right? So since it's not less than this, we know that this won't work, and we don't need to go to 0 from 4, right? So that's what's happening there. And then from 0, right, we then, or from 4, we have to iterate to 7 as well, right? And so we find that this distance is less than the 1 to 7, right? So, or this distance to 2 is greater than the distance to 4 plus 7, right? So we add this to the queue. However, right, since the minimum weight comes first, that 0 is going to reach the 2 first. Since we're going to add a pair to the priority queue that has 4 plus 1 plus 7, which is 12, and node 2. But when we have the node 2, when we're at the node 0, right, and we iterate to 2, then we're going to have 4 plus 5 plus 2, which is less than the current distance of 12, and replace it with 11, right? So, and this path is actually going to come first. So when we go to 2 now, the distance is going to be 11, right? And in the future, when we will try to go to 2 with the weight 12 that we added from 4, it's going to trigger this condition of finalized, right? And we just continue since we finalized it earlier, which means that there was a shortest path that we found earlier, and now we don't need to traverse it again, right? So that's how that part of the code works. And yeah, that's pretty much how it works, right? You also go to 3, but I don't think I need to explain that again. So yeah, that's how this Dijkstra's algorithm works, basically. All right, so okay, so the next algorithm that we're going to be going through today is lesser used, but still like pretty good to know. It's called Bellman-Ford algorithm, right? And it's similar to Dijkstra's in purpose-wise, except for one point, that Bellman-Ford supports graphs that have negative edge weights, right? And you can use that to detect negative cycles. But it's a lot slower than Dijkstra's because it has a complexity of vertexes times edges, and as a result, it's rarely used. Normally, Dijkstra's can't support negative edges, right? Because then it could be optimal to like go backwards and stuff, right? So because you want to reduce the edge weight as much as possible. So yeah, so that's why we need Bellman-Fords. And obviously, in a graph with negative weights, negative cycles are a problem, right? Since if you have a negative cycle, you can just have every node go to that cycle and then keep running through the cycle over and over and over again. So you obtain a weight of essentially negative infinity, right? So that's why detecting negative cycles is pretty useful as well. So how does it work? Similarly to Dijkstra's, we initialize the array dist with all infinity, right? And it'll represent the minimum weight we need to get to dist from our source node. And we'll now repeat the process n-1 times because the longest possible path, which is like a straight line, has length n-1, where n is the number of nodes. In terms of edges, like n-1 edges. So basically, we just repeat the following algorithm n-1 times. For each edge connecting u and j, right, we check if distance to v is greater than distance to u plus the weight of edge, then distance to v equals distance to u plus weight. This is very similar to Dijkstra's check, right? This one right here. Except we just do this a lot more times. So let's go through the code. You have the same thing as before, right? Everything's infinity, and we loop through n-1 times, and for each of the edges, right, we try to optimize our distances. see if the distance from u plus the weight is less than the distance to v, right? And if it is, then we just optimize it with the distance, right? So, okay. And now we have to check for negative cycles. So basically, we can just run the algorithm one more time, right? And check if it's still not optimized. And if it's not, then we know there's a negative cycle because all the paths are at most length n-1. So if it's ever optimal to keep going on a cycle, like more than n-1 times, right, then we know that that cycle must be negative because why else would we want to keep going on it if it's positive, right? So basically, we just run the previously discussed algorithm of checking all edges one more time. And if there's anything not optimized, we just return negative cycle, which is just an array filled with negative infinity, right? Signifying that, like, technically the shortest distance to every node is negative infinity. All right, so the third and last algorithm I'm going to be going through today is called Floyd-Warshall's algorithm. And it finds the shortest distance to get from every node to every other node in a directed weighted graph. So, well, we know that Dijkstra's finds the shortest path to get from, one node to every other node, right? But Floyd-Warshall finds this for all the nodes, the shortest path between all pairs of nodes. And when is it used? Well, one example is like dense graphs, right? Usually you might think, like, why can't we just run Dijkstra's n times on every node, like for every node, right? Well, in very dense graphs, you can have up to n squared, or roughly n squared, more precisely, n times n-1 over 2 edges, right? In such graphs, Dijkstra's would take, doing n Dijkstra's would take n cubed log n, right? As opposed to the Floyd-Warshall's n cubed. So that's when Floyd-Warshall's might be more useful than like a normal n Dijkstra's. So the general concept is very simple. It's basically just 3 for loops, and I'll refer to them as I, j, and k, right? So for each I, we'll check if the distance from j to I plus the distance from I to k is less than the distance we've currently marked down from j to k. So basically, for each pair of nodes, we check all paths from node 1 and 2 and mark down the minimum one, right? So basically, for every pair of nodes, let's find a middle node, right, that is connected to the first one and the second one, and basically relax the distance from the first node to the second node with the first one to the middle node first, and then the middle node to the second node. So this is the code, like very simple, right? It's an adjacency matrix. It needs to be an adjacency matrix. Like adjacency lists won't work for this, but if you ever want to use this, it's pretty easy to convert from adjacency list to adjacency matrix, as for every edge, right, you just mark down, like, say you have an edge ij weighted w, you just say edge matrix ij equals w, right? Pretty simple. Then you can run Floyd-Warshall's here, and yeah, this is the code. It's pretty short and nice. And that's one of the reasons why sometimes it's used, is because it's like really short and clean and stuff. Okay. So here are some like practice problems. I think the PowerPoint might be somewhere you guys can access it afterwards. So if you want to, you can go on, you can check out these problems and try to do them, right, for good practice. And shortest paths is like very common in gold problems, especially. So if you like it's actually one of the most important things in gold. So yeah, mastering this will do you good.